let's look at this problem that is given to us. Over here, what is there? That is course schedule. Okay, so I need to schedule the course, but how? Let's look into it. Firstly, we'll be recognizing the pattern over here. Cool. So what is there? Here, there are total num courses that is given to us, and which I need to enroll into. So it's labeled from 0 to nums of course minus 1. That is, it indicates that it's a zero based indexing. That is, if there are 5 courses, so it will be 0, 1, 2, 3, 4, something like this. And what is the prerequisites array, which has prerequisites of I. Okay, what is the prerequisites? Over here I can see it's a 2D array, that is a matrix, and in that each element is 1D array, which has 2 elements provided over here. So let's say if prerequisites of I, okay, one 1D array defines what? Okay, it will be having 2 elements, A of I and B of I. It indicates that you must take course B of I first if you want to take course A of I. That is, in order to enroll into A of I1 course, BI is the prerequisites. Okay, for example, if I consider 0, 1, indicates what? That to take course 0, first I need to take course 1. In order to enroll in course 0, I should be well versed. I should firstly enroll in course 1. And if it's possible, I'll be returning true. And if by some chances, we'll be looking into the edge cases. In that case, I'll be returning false over here. So let's look into these examples. Okay, oh yes, precursors are 1, 0. That denotes what? Okay, let's take this example. So here, as you can see, something like this. Over here, what is there? That is, in order to do this course, first there are prerequisites that is 0. Firstly, I need to finish that. Okay, so it indicates what? That is, okay, I have 2 elements, and the first element is the course, and the second element defines the prerequisite which I need to finish in order to complete the course. Something like this. Oh yes, you can see this thing. From this I can see something like this. It denotes what? Let's say if I want to study Next.js, what I need to do? Okay, in order to study Next.js, firstly I should study React.js. And in order to study React.js, firstly I should be well versed with JavaScript, that is JS. And I should have some knowledge of HTML, CSS in order to be used to, in order to understand it properly. So there's a proper ordering I can see over here. That's what? That is, okay, firstly I should understand and learn HTML, CSS, and then I should go with the JS, and then I should go with the React.js. I should not actually jump to the React.js, so that would be uh, no, that doesn't make any sense over here. So, and after React.js only, I should go with the Next.js. So you can see over here that there are linear ordering it maintains. You can see that there are linear ordering, as you can see over here. That denotes over here. So linear ordering, that is, I need to do some task before some task, and there are some tasks before some task, something like this. So from this, what I can do, that comes to my mind. Okay, I can recognize. Okay, it's something like topological sort, which indicates what? In topological sort, what we does in topological sort, what we usually do over there, I say I can, if I can make linear ordering of whatever the nodes address in the graph, and there should be a u to v edge, that is u points to v, that is v has the inward edge of u, and firstly I need to do u and then v, so that is u should come v before v. That's what topological sort is. So I can do this topological sort using either DFS or BFS. If I will go with the BFS approach, DFS is easier, but just to explain you the intuition, just to explain you the thought process, I'll be going with the BFS approach. So there, I can go with the Kahn's algorithm. Kahn's algorithm. So from this, I can simply break every step, and I can make you think about it and why we are going with this particular approach. Okay, so we are determined that okay, why, and that topological sort is there, means how I can implement this thing. That's a different part. But okay, firstly I determine that okay, over here it's the pattern is somewhere like topological sort. If I can short it, I can determine okay whether I'm able to short it perfectly or not. If I'm not able to, that means there's something issue. In that case, what I would be doing, simply return false. Or if so, everything is okay, good, then I'll be saying okay, return true over here in that case. So that's the thing which I need to do. If you're not knowing about the topology sort or Kahn's algorithm, I'll be okay. So in order to solve this problem, there are prerequisites in topology sort, and understand a Kahn's algorithm, that is the PFS approach of the topology sort. Then only do this. That's a prerequisite over here. Okay. So let's try this out. So here, if you can see this thing, that is what over here topological sort. I want to implement topological sort. And over here, I'm gonna use the BFS approach. That is, I'm using the Kahn's algorithm over here in this case. Okay, cool, great. So what it says that okay, U to V has to be the edge where U should be before V. And over here, let's say for example, what is there? Let's say if there's a course 0 and 1, so it indicates what? Okay, first element is the course and the second element is the prerequisite. That means firstly I need to study prerequisite and then course. So firstly this has to be there and then this. That means over here in our case this is the U and this is the V, I can say. Okay, I can conclude something like this. Okay, course is the V and firstly I need to do U over here. Okay, so to make it easier, firstly let's create this relationship list kind of stuff. Okay, firstly have some, because over here what does adders have? Only the connection. Okay, to do this course, this prerequisite. To do this course, these are three prerequisites. There could be the case that one course has many prerequisites, and there could be the case that one prerequisites are the applied to many courses. Okay, so over there, let's say firstly create the list of this adjacency list. So here, what I'll be requiring, that is a list of integer. Means I'm not going in depth about this because you should be well versed. And over here, if I'm going to use topology sort and cars with all these things, so I need to simulate this. Okay, I need to relate it with the nodes kind of stuff, graph. Okay, so I can say okay, this is the graph problem over here. Okay, I hope you're getting it. So okay, so I need to represent in the adjacency list. Let's say I'll be naming it as ADJ, that is adjacency list, and then I'll be building the adjacency list over here by passing whatever the num courses adders have over here, that is this thing, and whatever the list adders have over here, that is a prerequisites list over here, adders have over here, I'll be passing that, and from that I'll be getting the list. Okay, so let's create the method of this. So private, what I'm gonna return over here this case, so it's the private, and I'll be returning this thing obviously because I'm holding adjacent list over here this case. And then okay, let's name it as I don't need to figure out that what should we name. I already figured it out. Okay, build adjacency list, and what are stuff I'll be requiring as a parameter, as I have passed the nums of courses and num prerequisites, so I'll be using that same as is over here. Okay, cool. So I need to return this list. So firstly create that in order to return that list. Okay, so it will be, let's say I'm using the array implementation, array list implementation over here. I don't need to specify the data type because from the Java 1.7 inference type inference, I can just simply take whatever there is on the left side. Okay, so I'll be firstly, I should have that number of lists. It's just a basic graph. I'm just creating an adjacency list. So what number of list I should have? List of list. I have this list. I need to create this list, and this has to be the equal to the number of courses adders over here. So let's create that quickly. So just iterate it from the number of courses, that is num courses over here, and I need to do what? I need in the adjacency list I need to add empty array list for each of the node, because each course could have many prerequisites, or each prerequisite can be the of for the many courses. Okay, so okay, now create the edge over here. So let's say, so prerequisite has each element was array. Okay, that is edge over here. Let's say I'm saying I'll be iterating over the prerequisites that adders have over in this case. Cool. So u is there. Let's say edge of over u is what at first index, or I could say, let's say edge of 0 is the u, and int of v is the what edge of 1. So this is the thing, but what I'll be doing, okay, adjacent of v, in v I'll be adding this u node over in this case, and at the end I'll be just simply doing this, keep on doing this thing for the all the previous data as have, and then return this adjacency list which I have just now created. Cool, is the thing. And now I'll be requiring indegree as well. So okay, how many integers I need to determine for all the nodes which I does have. Nodes here is courses, because now I'm doing it in the topological sort and Kahn's algorithm. So in that case, I need to simulate it. I need to represent it into the nodes. So okay, that number of nodes will be there. So what the number of nodes? Same as the number of courses that I does over here. Cool. So now I have to determine. Okay, so for each node, now I'm saying node has the course. For each course I need to iterate firstly. Cool. Now I have to say what course. Okay, if I need to say, okay, I just have the adjacency list over here. It's saying what u to v. Okay, oops, it's saying v to u. That is, there's the edge from v to u, so u has the inward edge from v. So I can say something like this. So I can say, for I could just, for the simplification, I'm saying, let's say u over here, u. Now for each v, I'll be saying each v from this u over here, that is u I'm iterating for each. Now from this adjacency list dot get for u, whatever the edge node you will be having pointing to v, so all the list which u has the inward edge from u. So that's the thing it's saying. Okay, so for that in degree, for that v node I need to increment the in degree over here. Okay, and I have to determine, okay, what all nodes has the in degree 0. That determines, okay, if in degree 0, so it determines that, okay, all the prerequisite course has been done or there is no prerequisite, so I can just simply add it over here. Cool. So for that I'll be leading a queue, because it's the BFS approach, and the BFS I need data structures helps queue, and in order to implement Kahn's algorithm, so I will be requiring the queue over here. So queue of integer, because integer is the number of course, because it's 0 to nums of num course minus 1, and that I'm determining over here. That is a node over here. So let's say I'm naming queue as q, and let's say I'm creating the implementation class of the linked list over here, something like this. Cool. So I'm gonna iterate for int I equals 0 for all the integers that is over here. In degree dot length, that is nums of course only. Degree in degree dot length is that only. So okay, whatever the in degree was for whatever the node, the in degree value is 0. If in degree of I is equals to 0, that's the potential answer that is over here. So I'll be offering for the queue, I'll be offering, okay, add this particular node over here in this case, and okay, that's done. Now while queue is not empty over in this case, I'll be implementing my logic. That is what, that is for, I'll be iterating for all of its neighbors. Okay, that is adjacency dot get for all of its neighbors. So okay, I need to pop out. So int I'll be having the current node. So q. So over here, for each of its neighbor nodes, I'll be iterating and looking into it. Okay, not looking into it. If I'm considering this neighbor, that means the in degree from u to v. Oops, in our case v to u is done. So I need to remove that in degree over here from this case. Okay, I need to do what? In degree minus of whose of this n node. minus minus, and during this process, if the indegree becomes 0, that's the potential answer in this case. That is, if indegree of the node n is has become 0, so that's the potential answer. I can just simply offer it to the queue. I will say, okay, queue dot offer this particular node. This is the potential answer now. Means I need to figure it out for the this particular neighbor node as well for now. Okay, this thing I'll be doing over in this case, and also I'll be saying, okay, from the start itself, I'll be saying, okay, I'll be needing a processed. What all nodes has been processed till now? Initially, let's say it's 0. Okay, so let's say initially no nodes has been processed, so the process is 0. So when I'm polling out that particular node, so that node has been processed. So I'll be saying, okay, processed, incremented, plus plus, and at the end I need to figure it out that, okay, if written that stuff, if the process number of nodes is equals to the number of courses that others have, that determines, okay, all the nodes has been processed. That means all the courses are properly arranged. They haven't manipulated us. That is, they haven't provided something like this. Okay, that is a prerequisite or something like this. Means 0 to 1. Okay, in order to do the course 0, there should be prerequisite. There are prerequisite 1, and in order to do prerequisite 1, there are 0 has the uh, uh, prerequisites. So in this case, this kind of manipulation is not there. That means if this is there, so in Kahn's algorithm, what will be there? Cycle. And if there is no cycle, in that case only the number of process node equals to number of courses over here in this case. Okay, so this is the thing that I need to tell you. So let's check this out whether it's gonna work or not. So let's try to submit it. Let's see this whether it's getting whether it's working or not. Okay, there are certain errors. Let's see that what is that. At line number 42, if we'll be seeing that, okay, oops, that's certain increment kind of issue, small issue over here. And now if I'll check, okay, it has been accepted over in this case. And let's say try to submit it as well and see whether it's getting submitted or okay, it has been accepted over in this case. So let's see you in the next video. Bye bye. Let's compute the time and space complexity quickly. So if we'll see that what is given to us, we maximize it. Over here in this case, if we will be seeing, okay, what does address have in this case? Okay, for the space complexity, address adjacency list. So the adjacency list will be what? That is the number of uh, courses, and the pairing, that is the v plus c, that is vertex plus edges. And over here in degree, that is the number of courses, this number of, that is big of v. Here it's big of vertex plus edge. Here it's big of vertex only. And what are they? Linked list. So each queue is getting processed at the max, that is big of vertex over here. So the space complexity is big of vertex plus edge, that is big of v plus c. If I will be saying over here, that is the space complexity over here, it's what? Big of vertex plus e in our case. And let's look into the time complexity as well. So what's the time complexity in our case? Time is what I'm doing over here, iterating. Okay, that is for each nodes, that is big of v, that is the number of courses, big of, that is the vertices. Same goes to here, big of vertices. And for each pairing I'm be looking, that is for each edges for each node, that is big of vertex plus c. So at max it will be same, that is okay, and big of vertex plus edge. Same goes to for the time complexity as well. Yeah, so if you know, if you can solve this problem, now you can easily go with the course schedule 2, course schedule 3. Okay, course schedule 3 you will be needing heap operation as well. So this is what I wanted you to understand, not just how to code, but how will it be coming with the topology sort and the Kahn algorithm. That is the thought process and the pattern that you need to recognize. So yeah, now bye bye.